Most insects die the moment temperatures drop below freezing. Ice crystals form inside their cells, shred the walls from the inside, and that's it. But there's one insect that freezes completely solid all the way through, and then just wakes up when it warms. No damage, no death. It walks away like nothing happened. And the reason it survives isn't magic or luck. It's chemistry, a specific, measurable chemical strategy that locks ice out of the cells entirely. Once you see how it works, you'll never look at a hard frost the same way again. You've probably seen what a hard frost does to a tomato plant. Not just wilting, not just drooping. The whole thing turns to mush overnight, stems and all, like the structure just gave up. Most people chalk that up to the cold killed it, but that's not quite what happened. What actually happened was mechanical destruction at a cellular level, and it's worth understanding because it's the same threat every living thing on Earth faces when temperatures drop below freezing. A living cell, at its most basic, is a bag of water. Not just water, right? There are proteins in there, organelles, all kinds of machinery running constantly, but the whole system sits inside a thin, flexible membrane, and that membrane staying intact is non-negotiable. Punch a hole in it and the chemistry stops. The proteins spill out, the gradients collapse, and there's no putting it back together. When it freezes, that membrane is exactly what gets destroyed. Water inside the cell starts to crystallize, and ice doesn't form as smooth, round shapes. It grows in jagged, branching structures with sharp edges, and as it forms, it expands, pushing outward against the membrane from the inside. Think of inflating a balloon that's already packed with broken glass. The membrane stretches until it tears, and once it tears, that cell is done. No repair, no recovery, just dead tissue. Now multiply that across millions of cells at once, all freezing at roughly the same time, and you get a tomato plant that looks fine at dusk and sits in a puddle of its own liquid by morning. It's not the temperature that kills it. It's the physical tearing happening too fast and too small to see. And this isn't a plant-specific problem. Every complex organism with real cells faces the same physics. Insects, mammals, any living thing built from cells with membranes, they're all equally vulnerable to this process. The ice doesn't negotiate. It forms, it expands, it tears. Surgeons who freeze tissue for storage know this well. The protocols they use involve specific cryoprotective chemicals, and without those chemicals, frozen tissue doesn't come back functional. It comes back as dead pulp. That's not a failure of technique. That's just what biology does when it freezes without protection. So when researchers first documented an insect that had been frozen completely solid and then thawed out and walked away unharmed, the scientific community's first reaction wasn't excitement, it was skepticism. Because everything we know about cell membranes, ice crystal formation, and what happens to proteins at sub-zero temperatures says that outcome shouldn't be possible. The data from 100 years of cryobiology points one direction, and a crawling, functional insect, after a hard freeze, points the other. Freezing kills because ice physically destroys cells from the inside. That's not a theory, it's mechanics, which is why the place this insect actually lives turns out to matter so much. There are parts of North America where winter doesn't ease in gradually. Temperatures drop hard, stay low for months, and anything sitting exposed in the open freezes solid, no negotiation. And that's exactly where the goldenrod gall fly larva spends its winter. Not underground, not tucked into any kind of shelter, but sitting inside a hardened, round growth on a goldenrod stem, fully exposed to whatever the air temperature happens to be. When it drops to minus 20 Celsius outside, the larva drops to minus 20 Celsius. No buffer, no insulation between it and the cold. Researchers have pulled these larvae out of their galls in the middle of January and put them on a lab bench to measure what's actually happening inside. Thermal imaging confirms it. Frozen, completely solid, all the way through. No heartbeat, no movement, no detectable metabolic activity of any kind. By every standard measure we have, the lava reads as dead. Not dormant, not slowed down. Dead. Then they warm it up. Slowly, over a few hours, the temperature climbs back towards zero. And at some point during that process, the lava twitches. Just once at first. A small movement, barely visible. Then it rights itself. Then it crawls. Fully functional, no apparent damage, behaving like an insect that spent the last few hours doing nothing unusual at all. The researchers who first documented this in controlled lab conditions didn't trust it, so they ran it again and again, freezing the same larvae multiple times across a single winter season. The majority survived each cycle, not a few outliers, not a rare subset with some unusual trait. The majority, repeatedly, across the whole season. What's strange if you watch it happen is that the larva doesn't do anything visible to prepare when the cold arrives. It doesn't curl into a protective shape, doesn't slow down gradually, doesn't signal in any observable way that something protective is occurring. It just stops, freezes, waits. That behavior, or lack of it, makes more sense when you consider where this insect evolved. In Arctic and subarctic regions, freezing isn't a bad year or an unusual cold snap. It's a scheduled event, every single winter, lasting for months. When a stress is that consistent over thousands of generations, evolution doesn't produce animals that cope with it badly. It produces animals that are built for it. The goldenrod gallfly larva isn't surviving in spite of its environment. It's a product of it. So we know it survives. We've confirmed that in controlled conditions, repeatedly. But survival without explanation is just a curiosity. And the explanation here is where this gets genuinely interesting. It's not that this larva has stronger cell membranes or some physical advantage we've missed. Something chemical is happening, and it starts well before the first freeze arrives, triggered not by cold at all, but by something else entirely. What's actually happening inside that larva isn't what most people guess. It's not antifreeze the way your car uses it, not some compound that drops the freezing point of the whole body below zero and keeps everything liquid. The strategy is more specific than that, and it starts weeks before the first frost even arrives. As days get shorter in late summer and early fall, the larva's body starts converting stored glycogen into glucose and a sugar alcohol called sorbitol. These compounds flood into the cells and into the fluid sitting between them. And here's what matters. This process gets triggered by day length, not by temperature. The larva reads the shortening light, not the dropping cold, and begins its chemical prep while it's still warm enough to do the work efficiently. Now, these sugars don't stop ice from forming. Ice still forms, the lava still freezes solid, but the sugars change where the ice forms, and that's the whole game. They pull water out of the cells before it can freeze there. So the ice that does form ends up in the extracellular fluid, the spaces between cells where there are no membranes to shred. The cells themselves become so concentrated with glucose and sorbitol that their internal freezing point drops low enough to stay liquid, even while the tissue around them goes completely solid. Think of it this way. The cell is a room, and ice forms in the hallway, in the walls, in every space between rooms. But inside the room, because of the sugar concentration, the temperature at which water would freeze is low enough that nothing crystallizes. The structure stays intact. Cryobiologists call this freeze tolerance, and it's worth separating from freeze avoidance, which is what most cold-hardy insects actually do. Freeze avoidance means producing enough anti-freeze compounds to stop any ice from forming at all. Freeze tolerance means accepting that ice will form, but controlling exactly where it goes. Two different strategies, and freeze tolerance is considerably harder to pull off. The glucose and sorbitol do a second job too. Proteins inside cells are sensitive to cold. They fold and unfold based on their environment, and at very low temperatures they can stop working entirely. The sugars coat those proteins and keep their shape stable, acting like a buffer between the protein and the cold surrounding it. So the larva survives because it redirects ice formation away from the cell interior and protects its proteins at the same time, using two compounds its own body produces from stored energy. It doesn't fight the freeze. It manages it, systematically, on a schedule set by the sun, rather than the thermometer. Winter, for this insect, isn't an emergency it scrambles to survive. The preparation runs on a biological clock, tied to light, and by the time the cold actually arrives, the chemistry is already done. So that's the full picture. Winter isn't life or death for this larva. It's a chemistry problem with a solution the insect runs automatically, triggered by light, executed in the cells, finished before the cold even arrives. The freeze happens, the damage doesn't. Next time a hard frost takes out your garden, somewhere in a dried-up goldenrod stem, a larva sits frozen solid, perfectly intact, waiting for March.